I'd like to try to summarize what we've done in class the last couple of days regarding graphing polynomials of higher degree order. I'm going to take you through a few examples and let you do some work on your own and see if you can't put all the pieces together. We're going to look at the function called y equals x squared, familiar parabola. What we're interested in talking about is how the graph behaves to the far left and to the far right. We're interested in what's known as its end behavior. In this case, the graph enters through quadrant 2 and it leaves through quadrant 1 as we read this from left to right. What's important to remember here is that we're dealing with x squared. The exponent is even, and as it turns out, every polynomial that has an even power as the highest degree term is going to behave this way. Your book refers to this as the leading coefficient test. We're looking at whether or not the exponent is even, and we're also looking at the sign of the leading coefficient. If you were to graph y equals negative x squared, you know that this graph would be reflected over the x-axis, and in that case the graph would enter through quadrant 3 and leave through quadrant 4. So even exponent and positive coefficient, 2 to 1. Even exponent and negative coefficient, 3 to 4. Let's look at another situation. What happens now when we graph y equals x cubed? Again, this is a familiar graph. This time the graph is entering through quadrant 3 and leaving through quadrant 1. What's important here is that it is an odd exponent and the coefficient is positive. Odd exponent, positive coefficient, it goes from 3 to 1, and if you were to reflect this over the x-axis, odd exponent and negative coefficient goes from 2 to 4. So the leading coefficient test allows you to predict the end behavior of these polynomials. The next thing we want to examine is what happens in the interior of the graph, and in particular what happens to the zeros or the x-intercepts of the graph. We're going to take a look at all three of these graphs, x, x squared, and x cubed, to demonstrate a certain idea. So here are the graphs, and all three of them have the origin, or x equals 0, as an x-intercept, or as a 0 of the function. Let's look particularly what happens with the way it passes through 0. Y equals x, the straight line, simply goes right straight through 0, 0. Nothing fancy, no turns, just goes through it. Y equals x squared is tangent to the x-axis at this point. That is, there's a turning point here. It turns around and it goes back in the other direction. There's a point of tangency at x equals 0. And with y equals x cubed, you can see that the graph flattens out a little bit and passes up. So it goes through, it flattens out, it passes through the x equals 0, and it continues in the same direction. We're going to call that a point of inflection. Y equals x has an exponent of 1. Y equals x squared has an even exponent. Y equals x cubed has an exponent of 3, or an odd exponent. When we look at graphs in the future, if we see a factor that has an exponent of 1 it is going to behave this way at its 0. If we see a factor that has an exponent of 2 or 4 or 6 or 8, it is going to have a point of tangency at its 0. And if we see a factor that has an odd exponent, 3, 5, 7, 9, it will have a point of inflection at the 0. So here's an example where we can put all the ideas together. X times x minus 2 times x plus 2. First of all, in order to talk about end behavior, we have to know what the leading coefficient and the power of the polynomial is. If we were to multiply this out and look only at the x's, we would have x times x times x. So this is x cubed. It's an odd power. We expect the end behavior to enter through quadrant 3 and leave through quadrant 1. Let's look at the y-intercept because that's easy to find as well. If we let x equal 0, we have 0 times negative 2 times positive 2, which is 0. So it should pass through the origin. If we set each factor equal to 0, we will get the zeros of the function, which means we'll have an x-intercept at 0, plus 2, and minus 2. Because all of the exponents are 1 for each of the factors, we expect the graph to do nothing more than just pass through those points with no turning at those points. Let's take a look at the graph. So you can see it enters through quadrant 3, it passes through a 0, it has to turn around and come back down to pass through this 0, it has to turn around and come back and pass through this, and it leaves through quadrant 1. The next example is x times x plus 2 squared. If we were to multiply this all out, we would have x to the first times x squared, x cubed. It will behave as the last one did, entering through quadrant 3 and leaving through quadrant 1. The y-intercept should be 0 times 2 squared, which would be 0. So again, it will pass through the origin. This time we have a 0 at x equals 0 and x equals negative 2. Because the exponent here is even, when the graph gets to negative 2, we expect there to be a point of tangency. When it gets to x equals 0, we expect the graph to simply pass through that point. Let's see what the graph looks like. Enters through quadrant 3, point of tangency at negative 2, has to turn around and come back through 0, and it leaves through quadrant 1. You are not expected to know where that turning point is. You're just going to have to make it happen someplace. Next example, x times x minus 2 cubed. Multiplying it out, we will get x times x cubed, which is x to the 4th. X to the 4th is going to enter through quadrant 2 and leave through quadrant 1. It will have a y-intercept again of 0. It will have zeros at 0 and positive 2. Because the exponent is odd, when the graph gets to positive 2, we expect to have a point of inflection. We expect the curve to flatten out slightly and then continue in the same direction. Let's see what the graph looks like. So entering through quadrant 2, passing through 0, turning around, flattening out slightly at 2, and finishing in quadrant 1. Final example, a little more complicated. We have x plus 2 squared and x minus 1 cubed. If we multiplied all of this out and looked at the x's, we would have x squared times x cubed, which is x to the 5th. Odd exponent, we expect it to behave like x to the 3rd. Enters through quadrant 3, leaves through quadrant 1. If x was equal to 0, we would have 4 times negative 1, which is negative 4, so the y-intercept is negative 4. We would expect a 0 at negative 2 and also at positive 1. At negative 2, because the exponent is even, we would expect a point of tangency. Because the exponent is odd over here, we would expect at x equals 1 for there to be a point of inflection. And that's exactly what happens. It enters through quadrant 3, point of tangency. We can't see the whole graph, but it will turn around here. The y-intercept, I'll change the window. There we go. So quadrant 3 turns around with a point of tangency. It has a y-intercept of negative 4. It flattens out, and it leaves through quadrant 1. So that's an 11-minute presentation to try to encapsulate what we did in class over 2 periods. You'll have to try some examples. You'll have to try to get used to some of these ideas on your own, but hopefully that will be enough for you to make your way through at least some of the exercises that I'm asking you to do for homework over the long weekend.